Yeah, I think it started. So yeah, go on.
Okay. So hello everybody. Good afternoon. I'm Andrew. I'm from Group 5. We call ourselves Core Dump. And the paper we're presenting today is Muontrap, preventing cross-domain Spectre-like attacks by capturing speculative state. So most of the pictures in this presentation have been adapted from the paper itself, unless otherwise mentioned, where I mentioned it in the footnote. So the agenda for today's presentation is firstly we look at the problem itself and why you should worry about it. Then the solution, muon trap, some more nitty gritties about the solution. Towards the end, we'll see some results that show that we're not bluffing. It actually works. And yeah, at the end, we'll have a Q&A, so we can have questions. We can have questions through the presentation as well, uh, and we'll have a Q&A at the end, so it works either way. So first up is the problem. So we're all very familiar with these two logos today. It's Meltdown and Spectre. So these rocked the world basically back in 2018 when it was announced that these attacks basically affected every modern processor, right? So Meltdown and Spectre both exploit crucial or critical hardware vulnerabilities, and hence they're not easy to mitigate either. But over the past few years, we've seen mitigations for Meltdown, but Spectre is still scary, right? Because software mitigations haven't really been very successful. And that is what we are going to focus on. We are going to focus on Spectre, the scary part. So why should you worry about Spectre? If you're a person who isn't really into the whole security domain, you've probably not even heard of Spectre. Or maybe you remember a news article from back in 2018. So why should you worry about it? Well, you probably know this robbery scene from The Dark Knight. So you always worry about whether your money is safe in your bank, right? And you'd be worried if there are a bunch of robberies happening around the city and banks are losing money. Well, today that's not the real bank robbery that happens on a day-to-day basis. It's more of this format where your bank is logged in on one tab of your browser and your robber is in the other tab, and you can using Spectre, for example, the robber can steal your details or bank account details just using JavaScript, unless some mitigations are in place. Yeah. So this should give you a sense of why this is such an important problem and why solving it is critical. Right. So now let's go into a bit of the background. So basic on how Spectre works, just one slide. So the program, we've already seen this before. So Spectre, it requires a shared cache between attacker and victim. So how Spectre works is first the attacker primes a part of some data into their cache or brings data into their cache. The second is the victim is tricked into bringing a secret value into their cache, right? Under speculation. They load it. The third is followed by a second load, which is based on the first load's contents. That is, using the secret here stored by the victim speculatively, we do another load into the primed cache of the attacker. And then by reading whatever was changed in his cache, the attacker can then decipher what was the secret of the victim or some information about the secret of the victim. Um, so that is the crux is that for Spectre to work, you need access to speculative data across domain boundaries. In this case, it's across the boundary which is shown here, which is basically victim cache and attacker cache and the boundary between them. In general, it could be between browser tabs in the first example that we saw, or between processes, right? And this is an example of this is what we've seen in class, which was the array using out of bound indices for array 1, and then using that to access another value in array 2, which is stored somewhere in the attacker's cache. Okay. So now, so basically, if the crux is that you're able to access speculative data across domain boundaries, the solution should be to maintain domain boundaries between processes and prevent access to speculative data across these boundaries. And that is exactly what Muontrap promises. Right? So this is what Muontrap promises to achieve. Before we jump into Muontrap, there are a few existing solutions. The most famous of which is the InvisiSpec family and the STT set of algorithms or set of solutions. But they have some limitations in that the InvisiSpec family does not address leaks from the instruction cache in the prefetcher. We will see how you can leak data using these two in the slides coming ahead. And in this respect, Spectre, which is one particular part of the family, in fact had a very large hardware overhead, right? The other one, speculative tail tracking, this actually works by restricting the forwarding of speculative load values. So it doesn't even let speculated data go out of the process. And this causes a huge drop in performance, especially when there is complex memory access patterns. So again, we'll look at how Muontrap, our solution, addresses this. So our solution called Muontrap. So this is the usual computer, like this is the hierarchy usually. The CPU, we have the L1 cache, the L2, and the memory. So now what Muontrap suggests is add an extra cache somewhere which stores all the speculative data. So there is every speculative data for this particular process or thread would be stored in that particular cache alone, and it would not leave that cache. And hence, we claim that doing so will prevent Spectre, right? So our suggestion, add a small filter cache. So we call it a filter cache. It filters speculative data. It doesn't let speculative data leave and reach the L1, L2 or memory, right? That is fast and easy to clear and place it at the L0 level, right? So all speculative data is to be placed here. So this is the filter cache. So it's we've represented it by f small f d. So this is the filter data cache. So for data, so it's a small cache, and because it's very small, you can also maintain bit registers for every cache line, which maintain the validity of the cache line. And hence, it is so small, in fact, that you can invalidate a full cache in parallel, right? So if there are, for example, 8 cache lines, that's the effective size of 1 byte for the valid. So it would be a valid byte, for example. So you could just load one value into that valid byte, and you could you could invalidate the entire cache, right? So one key thing, the first step that we take towards our promise is to wipe out the filter cache on context switch. That is, when you switch from one process to another, or from the one process to kernel memory, kernel domain, then this is basically a context switch, and we wipe it out on such context switch. So this is the first step towards keeping our promise. Another thing we do is we virtually tag the cache simply because it's small, so it's easy to do that. And because we provide this guarantee that on context switch, we wipe out the filter cache. That means there is no question of aliasing of addresses, and hence we can virtually tag it. Right? So these points will become clearer as we go ahead. So the first is, how we keep the promise, the characteristics of the cache, inclusive, exclusive, or neither, right? This is the first thing we saw about caches, and that's the first question we'll answer. So let's assume that the cache was inclusive, for example, right? So let's see if an attacker could get the data from the victim. So if the cache was inclusive, let's say the attacker primed the L1 cache, right? And this was followed by the victim loading a secret into his own cache, which is now stored in the filter cache because it is done speculatively. And finally, using this data to indirectly evict from the L1 cache by modifying the filter cache of the attacker. So if you see here, so using the secret from step 2 to indirectly evict some data or modify this cache that was primed by the attacker by modifying data in the filter cache, right? So if it was inclusive, then this would happen. And this would allow the attacker to gain information from the secret filter cache. Similarly for an exclusive cache, right? And hence, the first decision we take is that the cache will be neither inclusive nor exclusive. The filter cache is neither exclusive nor inclusive, right? We place another thing with a guarantee, which is write back through the filter cache is done only on instruction commit. So what we mean by instruction commit? So instruction commit is when an instruction is running speculatively. At a certain point in time, we will realize that the instruction is actually valid, the branch was actually valid, or if we have to discard it. In the case that the branch that caused the speculation turns out to be valid, then that instruction is said to be committed, or the path that was followed is a valid path. And on instruction commit, that is when we do a write back from the filter caches to the higher caches. Right? So now we're seeing that we're trying to keep the speculative data inside the filter cache as long as we're unsure if this path that we're following of instructions is going to be speculative only or it's valid. So this is our first step. The second step towards keeping the promise, the cache type. Another thing that we look at is who do we filter? So do we only filter the data cache, or do we probably need to filter, say, the instruction cache as shown in this page, right? So it turns out that we need to actually filter the instruction cache as well, and I'll show you why now. So let's say the attacker was to prime the instruction cache, right? So the attacker primed the instruction cache, then by they could trick the victim into loading a secret, which where the secret is used to index into the instruction cache using an indirect branch, right? So the attacker primes the instruction cache, the victim loads a secret, and the secret is used as the index to index into the instruction cache of the attacker using an indirect branch, right? And this would mean that basically, again, you're able to gain some information about your secret through this instruction cache. And 1 second, animation, yeah. So no, so the filter cache is needed for instructions as well. It should also be, in fact, if you think about it, it should also be used for the TLBs, right? Because if the TLB is to be filled with translations based on the speculative execution, that means that if you read the TLB, you can back calculate what speculative instruction may have caused a particular entry in the TLB. And hence we maintain a filter cache for the TLB as well, right? Or a filter TLB, FTLB. Yeah. So, okay. Right. So the next question is, are there other ways to that speculative data can be leaked? We've looked at inclusive, exclusive. We've looked at whether instruction cache, filter data, or any other parts of the microarchitecture have to be cached, given a filter cache, right? So are there other ways of leaking speculative data? Well, this was actually part of the slide on existing solutions. So we mentioned the prefetcher and we mentioned the prefetcher, right? So the prefetcher, in fact, can leak speculative data, and so can the cache coherence protocol, which was, yeah. So the cache coherence protocol, we'll look at a few slides from now. So let's look at how we can handle the prefetcher and what kind of attacks you can get through the prefetcher, and what Muontrap does to prevent a Spectre-like attack on the prefetcher. Right? So the first thing we do is we prime the cache, and then you prime a cache that features a prefetcher. So let's assume the L2 cache has a prefetcher, and then follow this by loading a secret, right? As always. So the victim loads a secret. Now the victim then loads an address to trigger the prefetcher to bring the next line into a non-speculative cache, right? So because of some secret that is here in the filter cache of the victim, the prefetcher reads this, and that triggers modifying the L2 cache of the attacker, right? And this way again, you can the attacker can back calculate and gain some information about the secret. So to clarify, the attacker primes the some non-speculative cache that is shared. The victim loads a secret, and based on the secret, the prefetcher modifies the primed cache, right? And so, what was the root cause of this? Again, it is the prefetcher's access to speculative data, right? Or instructions being executed speculatively. And hence, we suggest prefetch only using the committed instructions, right? So do not prefetch using speculative data. Instead, prefetch only using committed instructions. How we do this? We track the original, the parent cache, or the parent level cache of the particular cache line in the filter cache. And once that particular cache line is committed, the data in that is committed or belongs to a committed instruction, we call the parent's prefetcher on the instruction commit, right? That is, we load data from some higher cache into the filter cache. We maintain track of the parent cache, right? And once that particular cache line is committed, then you inform the parent cache that, okay, now you can prefetch based on this data, the data stored in this cache line. Yes. So this is how we protect the prefetcher from speculative Spectre and related attacks. So again, the same mantra as always, which is don't let others see speculative data unless committed, right? Until committed. The last attack was cache coherence based attacks. The last way we're looking at. So a little bit of background on cache coherence. We've already done this in class, but a slightly more advanced version of, I mean, a more later version of cache coherence is used. The protocol used here is the MESI protocol, as shown here, MESI. So cache coherence, as you all know, is the uniformity or is maintaining uniformity of shared resources that end up stored on different local caches, right? So you need to ensure that if you have multiple copies of the same variable in multiple local caches, you should ensure that all those local copies have the same value, right? Or at least the ones using the local copy know that it's an invalid value, right? Or any of those. So MESI is refers to 4 states that each cache line can be in. M refers to modified, which means the cache line differs from main memory, right? That is, the value stored in that particular cache line differs from main memory, and this is the only copy in the cache hierarchy. So there are only 2 copies in the entire system, one in main memory, one in the cache hierarchy, and they are different. So this is what M denotes. E, or exclusive, is similar to M in that it means that that cache line is the only cache copy in the hierarchy, but the value stored in the cache hierarchy is the same as that in main memory. S implies the same as E, except that there may be multiple copies in the cache hierarchy. And I is the invalid bit or invalid state. If it denotes if the line is invalid. So these are the states that cache coherence protocols suggests.
So it seems there is a glitch, right?
Yeah, I think he got disconnected.
Mm-hmm. Is he online? No.
Sir, it's a network issue on his side. He'll be joining presently.
Okay, okay.
Hello. Am I audible?
Yes. Yeah. I can
Sorry,
hear
sir. I think there's some internet issue in our floor.
you. No issue.
Sorry.
No issue. Go on.
So I think the MESI protocol was conveyed, right?
You have to share your screen again.
Yeah. So the MESI protocol was conveyed. That came across, right? So, uh, did I lose internet after this slide? That is what Teams told me.
Okay, you are explaining this last point, invalid, and then
invalid.
Yeah.
Right. Okay. So I'll keep my video off because now I'm on mobile data.
Sure.
So as I was saying, so in the last state that MESI protocol suggests is the I state or the invalid state, which is the state in which a cache line will be if it is invalid. For example, if you have shared lines and let's say one of them gets modified and you maybe before you modify the others under some setup, you might decide to just invalidate all the other copies of the cache line. Okay. So that in that case it would be I. So now looking at an attack based on this cache coherence protocol. So in this case, what we do is the attacker primes the cache on his side with the load, right? So load X, and what happens is X now goes from an invalid state to the exclusive state because X has now been copied from memory. It is the only copy in the cache hierarchy, and it has not been modified. Yeah. following this, you trick the victim into loading some secret, called, let's say it's called Y, and using that secret, you trick them into triggering a load. Now, load X in this case will become from I to S because it's a shared copy. Now, there are two copies in the hierarchy, one with the attacker, one with the victim. And now, when the attacker tries to store into this copy, now the shared state has to change into the modified state, right? So the thing is, what if there were no shares? If the cache line wasn't shared between the attacker and the victim, then the modify instruction would not, so the store instruction would not have to go and invalidate the copy of the victim. So in this case, once you try to store into X on the attacker side, it takes extra time. The system takes extra time to go invalidate the cache line on the victim's end. So by doing so, by measuring the time, we can decide if the victim had a copy of the secret or not. And backtracking again, you can decode the secret or some information about it. Right. So that is the speculative instruction accessed data that was initially in the E form, right, in the cache hierarchy. So the secret was in the E state. And because of this, it became shared and hence the secret was leaked. So what we do, the solution is to reduce the cache coherence for speculation alone. So while speculating, we're going to reduce how coherent the cache is, and that is by doing this. So we put a condition that the filter cache can only hold data in either the I or S form, right? And hence you will not be accessing any data which was in a filter cache in the E form, right, or in the M form. And also we put a condition that speculative memory access is not allowed to modify the coherent state of non-speculative caches. That is, speculative execution will not modify the coherent state, that is M, E, S, or I, of any non-speculative cache. So this way we are making sure that the effects of speculative access do not go outside the filter cache, right? So as an example, if this was the state at some point in time, we have the L2 cache, two L1 caches of two processes, and the filter caches. So now for the filter cache on the left, the filter cache here, which of the states are accessible? Basically, all the states in green are accessible, right? So any cache line on the direct path to the higher cache, that is accessible to the filter cache. Okay? So also any shared cache lines in the other process cache. So all these S states are accessible to the filter cache, but this particular E state or this M state, the modified or the exclusive states, those are not accessible to our filter cache under the protocol we are suggesting. Right? And of course, the filter cache on the other process is completely unreadable. Right? That is our guarantee that you cannot, no other process can read the filter cache. Yes. So by doing so, we see that only exclusive modified on this direct path or shared or invalid from the right side can ever interact with our filter cache. Thus, we cannot spread any or leak any data about our secrets to the other side. I'll just turn off the laser pointer. It's very slow on my laptop. Yeah. So we've seen a lot of steps that we've taken or protection mechanisms added to the filter cache to our filter cache to prevent leaking of speculative data. There are a few things that Muontrap, the solution, does not address. One is data visibility. That is, it does we do not clear. So the question is, should you flush the filter cache on misspeculation, right? So what Muontrap does is it does not clear the filter cache on misspeculation simply because the cache data during misspeculation is often reused and is vital to performance, right? So in this case, a process can read its own filter cache after correct execution starts, even if the cache was filled with data based on a misspeculation. The second is contention. So the effects of speculative data being evicted due to the small size of the filter cache. So the filter cache is very small, and as mentioned in the start, is a small cache. And what happens if speculative data is evicted, right? In this case, in the undersized filter cache, speculative data may be evicted before commit time, and so data maybe have to passively, data has to be reloaded from some higher cache or memory into the L1. So this causes transient contentions. But Muontrap does not address this simply because to take advantage of this contention, both victims committed and speculative execution are required. Arbitrary access to both of these are required. And hence, they believe it is out of scope. The paper claims to be out of scope. The third is timing. So again, should committed code be able to observe timing behavior of concurrent speculative execution on the same thread? So this is another question that Muontrap asks. And their suggestion is to use barriers and flushes to mitigate this. Right? So they do not incorporate it into this Muontrap solution directly, but instead ask for barriers and flushes to be used to prevent such timing attack. So yeah, any questions so far? So this is about the Muontrap itself and how it was built. So a step-by-step building up of Muontrap. After this, we'll move on to results.
I think you can finish
Okay.
the results and then we can have the Q&A.
Yes, okay. Yeah. Before we look at the results, this is the setup that the paper has used. So I just like to point out one thing here, which is crucial to the results that we see later. It is that now because so the L1 cache, the data L1 cache had a 2-cycle hit latency, right? But now because we're including a filter cache in the path, the filter cache itself has a 1-cycle hit latency, and hence an L0 miss plus an L1 hit now has a latency of 3 cycles. Right? So this slowdown leads to some performance drops that we'll see in the coming results. So this is the first set of results. This is on a benchmark called the Spec CPU 2006. So we have the 5 methods here on the top: Muontrap, InvisiSpec Spectre, Future, and STT Spectre and Future. So these are what we saw at the start. What we observe is that Muontrap Muontrap slower than no L0 cache by around 4% on average. That is, the normalized execution time on this scale, 1 denotes the execution time in the case of the normal cache hierarchy. That is, there is no filter cache. There is the usual L1, L2, etc. Right? And therefore, we see that on average, Muontrap is slower than that implementation by about 4%. It is similar to InvisiSpec Future. So if you can see here, InvisiSpec Future is the dark green, and our Muontrap is yellow. So if you see across the graphs, the yellow and dark green will be similar in multiple benchmarks. So each of these is a benchmark. This is because both of them make speculative data visible only on instruction commit. This is one of the guarantees that Muontrap provided. Right? We see that. Right. And it is also better than STT, as it can handle more complicated speculative load chains. So in STT, as mentioned in the start, STT prevents the sharing of speculative data completely, whereas filter cache does still take part in the cache coherence protocol, the prefetcher, etc., through some modifications, and hence it is able to better track a complicated set of speculative loads or memory access patterns that STT cannot. The second set of results are quite interesting. This is the results on another set of benchmarks called Parsec. So in this, we observe, in fact, approximately 5% speed up by Muontrap as compared to the normal cache hierarchy implementation. This is because in Parsec, the benchmarks in Parsec have parallel workloads that actually are very amenable to a small filter cache. So having a small L0 cache with very low latency, in our case, a 1-cycle L0 cache, is very useful to the particular benchmarks in Parsec. So an easy summary of the results we see on this particular graph is basically on the right. So that is, STT Future causes a 38% drop in performance. InvisiSpec Spectre, a 28% drop in performance. STT Spectre, 18% drop, but Muontrap, a 5% increase. Right? All of this is compared to the baseline, which is the regular cache hierarchy implementation. The third is we saw the filter cache, and I kept saying that it's a small cache. But the question was how small and what is the optimal size, right? So as we can clearly see in this graph, we've varied the cache size of the filter, and we see the execution times at very small cache sizes, 64 bytes, 128 bytes. The execution time is quite bad, simply because it's so small that data keeps getting evicted and the performance drops drastically. On the other hand, as you keep increasing the size, this is on parsec again. So as you keep increasing the size, you see that performance improves. As mentioned earlier, parsec benefits from this small, low latency L0 cache. Right? So decreasing filter cache size implies more eviction in the filter cache and a drastic performance drop. Right? And we observe that at 2 KB, the 2048 bytes here, the 2 KB is optimal, and you achieve approximately 7% speed up on average. The last slide, this shows this last set of results. This shows the individual performance effect of different protection mechanisms used on the performance. So that is the base. If you just add, so we have the baseline, this line over here, the line at 1. Then you have insecure L0 on top, which is you just add an L0 cache to the hierarchy and do not add any protection mechanisms. Further going ahead, so just adding filter cache, including coherency protocol, the instruction filter cache, prefetching, etc. So all of these steps are shown here, and you can see the effect on the execution time of adding each of these protection mechanisms. One I want to draw our attention to is this parallel L1D. So that is a question was also raised. Why not have the L1 cache and the filter cache run in parallel or make the accesses parallel? So we observe in fact that configuring systems to access them parallelly leads to just a 2% overhead compared to a 4% earlier on the performance. Right? But this of course needs more work and redesigning in hardware. Right. So that's it. So that brings to the conclusion of the presentation. So what we've seen today is that Muontrap mitigates Spectre and its variants with minimal hardware overhead, right? Without removing this speculation. So unlike STT, which kind of prevented forwarding of speculative data, this does not remove that speculative execution, and it introduces this filter cache. We see the architecture here. You have filter caches for the instructions, TLB, and the data. You see the prefetch. So this is basically the channel across which you tell the parent, you inform the parent cache that okay, now this particular cache line has been committed. So you can use this to prefetch data. Right? We achieved approximately a performance drop of only 2 to 4% in using Muontrap compared to 10 to 40% over various methods seen in the past. And performance actually improves in benchmarks like Parsec, where you are able to utilize small, low latency caches. So that is the conclusion. Thank you. If any questions, we can take them now.
Hi, Tejeshwar here.
Yeah, hi.
Can you explain what happens when the data, speculative data, is evicted from the filter cache?
Okay.
Will it go back into L1, L2, or where will it go?
So you'll have to reload it from memory or higher caches into L1 on eviction.
So L1, L2, and shared caches still can have some speculative data available.
Right. So that is why this point came up, this contention point. The thing they observed is that it is this is the case only for a very small number of cycles. Right? And that is how they said that, okay, let's not focus on this too much. That is
what do you
I've
mean by
understood.
small number of cycles?
As in this data, the data from the filter cache, that would be yeah, so that would be in those higher non-speculative caches for a very small amount of time. That is what I've understood from the paper at least. Oh, okay. So it'll be for a very small amount of time, small number of cycles generally, and hence you shouldn't be able to use it. Is the conclusion I've come up with from the paper.
So you are saying data will be in the filter cache for only small amount of time?
No. Data is so once evicted, right?
Okay.
So data is in the filter cache. Normal processing is going on. In case of eviction,
Okay.
the new data has to come from the memory or the L2 to L1 and then to the filter cache. Right? It has to come back from main memory. Right. So this it will stay in the L1 cache for a very small amount of time. Is the reasoning that was given for letting go of this problem. It will stay for a very small amount of time in the L1 cache, not filter.
But the okay, so L1 is private, so it doesn't really matter if it is in L1, right? We are worried if it is there in the speculative data is there in the shared cache, right? Which is the last
Or you
level
can
cache.
cause effects from that in the shared caches. Yeah. So this is basically so. Right.
No. So L1 is private, but on a context switch, it can create a Spectre-like attack, right?
Yes, sir. Yes, sir. So,
Okay, yes.
yeah. So what they said is, what they say is, let's have it come to the L1 cache. It'll be there for a very few cycles, after which it will be taken into the filter cache. So this is it's so small that they called it a transient contention. And because it is transient, they decided not to address it. Okay, so this is one of the negatives we actually mentioned for the paper. So we mentioned that, yeah, you could still probably make use of the data there. During that small contention period, the data is in the L1 cache. So that is still insecure. And that was, I think, one of the negatives that we mentioned is that. Hello? Hello?
Yeah, go on.
Oh, no, that's also.
Hello.
Yeah, so we also say it's a negative. Yeah. Hi.
Yeah, this is Prajwal.
Hi.
While writing back, while committing, do you write the whole filter cache or just
No. Only
some?
the data that is related to committed instructions. So if particular cache line is related to instructions that have been committed, then that cache line is written back.
So along with tag, do you also store the program counter that bring that data?
Sorry.
So along with the tag, do you also store the program counter that brought that data?
So we store everything that would happen in a normal. So whatever would have happened had it been a non-speculative instruction, the exact same data is stored back into the cache hierarchy. In
No,
our case,
Andrew. What he's asking is, in the tag store, do you store the program counter information?
Oh, I'm not sure, sir. So
what do you think? Do you need to store program counter? No need to go back to slides. It's okay.
Okay. Yeah. Okay. Yeah. Should be still program counter.
So the question is, once an instruction gets committed, then only you write through the data to the lower levels, right?
Yes, to the higher.
So Prajwal's question is, do you store the program counter because of which you know that okay, now this this particular instruction is committed?
Sir, since only single process is running at a time, I don't think we need to store the program counter. It will be freed on process context switch.
Forget about context switch. It's just a design choice, right? Like, how will you know when the particular instruction is committed?
An instruction comes along with it. It brings a tag along with it, right? We can store we can map it to the ROB location or something, rather than storing the program counter, which is very big. ROB
Yeah. So basically, this is a small cache, right? So you can assume this is sitting closer to the ROB, and whenever the instruction gets committed from the ROB point of view, right?
Yeah.
But still, it's not clear unless you store it. How will you know?
Right. Okay. Yeah. So then probably should store. I would assume it stores.
No, then it will be super costly, man. It's not that simple.
Okay, so that's what I'm not very sure about this. I'd probably have to read more and get back.
I think the paper says they use a commit bit per cache line, which is set once the instruction is committed, right?
Yes, sir.
But that just says whether the line is committed or not. It does not have any address or location.
In the prefetcher.
Don't bring prefetcher here. We are just interacting with the processor. How do you know that the instruction is committed, and how do you communicate that information to the filter cache?
Okay, so the bit is there, the commit bit, but other than that, I'm not sure about the program counter being stored.
Maybe
I'll have to
along,
read up on that and get back.
maybe in the ROB Biswa, we might be storing the set ID and the way ID of that particular instruction and key, because that will be smaller than storing the entire PC.
I guess, yeah, something of that sort, yeah.
Yeah.
There should be a mapper, right? That says that, okay,
Right.
this instruction is present in this set number, this way number, something of that
Yes.
sort.
Right.
Yeah.
Yeah. Okay. So I'll read and get back on that. I'm not sure right now.
I don't think the paper has mentioned. I have read this paper.
They haven't mentioned it. I remember not seeing it. No, I'll read a bit more. Like I'll just Google and like spend some more time thinking, or maybe find their code or something, and then go through that.
Yeah, it's actually a good question. What Prajwal asked. Okay, what else?
Hello.
Yeah. Hi.
Yeah, sorry, I got disconnected. So my other question was, so the prefetcher is working when you commit the instruction. So as a one possible extension, can you prefetch from this this filter cache and store the prefetch instruction only in filter cache?
Yeah, so
Would
that
that
was
work?
an extension we suggested again. So in our review, that is one of the extensions we suggested. So design a prefetcher specific to this L0 cache alone, the filter cache alone, and it fetches based on the speculated instruction stream. Yeah, so that is something we've also suggested. And again, we'll ensure that the prefetcher fits like others to that filter cache coherency protocol that was suggested.
Yeah. So do you bring every data into this filter cache? How do you identify whether that is speculative data or?
I mean, so whenever a branch or anything for that matter, so we know, right? So once in the hardware, when you do take a speculative branch, the hardware is designed so you add a small, so you basically modify the hardware slightly so that all that data goes into the filter cache.
But Andrew, what Prajwal is asking is pretty subtle.
How do you identify if the data coming in is part of this or not?
Yeah, so
I think that would again come back to the previous question of having a commit bit or not. So
no. This question is completely different. What he's asking is, what is your definition of speculative instruction?
Okay, yeah. So that is any, for example, any branch in our usual case, if some
No, don't answer. There are so many tricky points.
Okay.
What you are answering is a textbook answer. Okay, so anything after a branch, right? In reality, it's not the case. That's why there is this tricky keyword called transient.
Okay.
So an instruction can be speculative, but it may or may not be transient. And the meaning of transient is, see, speculative can become, a correct path instruction eventually, right?
Right.
Yeah, if the branch predictor does a good job, BTV does a good job, let's say whatever, your exception, whatever is happening, but finally it turns out that, yeah, you are actually on the right path, correct path, not the right path, correct path, right?
Yeah.
Then that's actually not a cause of concern for these attacks, right?
Right.
The instructions which are actually speculative, but they eventually turned out to be false, right?
Yeah.
Like the path that you have entered into in terms of control flow, it's actually a wrong path.
Those are the cause of concern.
Yeah, those are the cause of concern, and you need a more sophisticated way to identify them. The simple bookish way won't help.
But sir, from my understanding, at least every instruction that comes on, like every speculative instruction and the related access, is all pushed into that filter cache.
That is okay. That's what I'm saying. As a high level 10,000 feet view, that answer is correct. I'm not saying it's incorrect. Okay.
Okay.
But if you want to be more precise, you should redefine it.
Okay.
Yeah. Because otherwise what will happen, you know, your speculative instruction code space will bloat. Okay. If you start marking all the instruction that follows a branch as speculative and then you put them in filter cache, the filter cache will just thrash. Okay. Okay. Yeah. So you should be pretty, you know, precise in your definition, like what exactly is speculative or transient that actually create this Spectre kind of attack. So that definition itself is a paper actually. Okay. Yeah. So then, President, I'll probably read that paper. And again, yeah. As no, I don't think you should read it because it's like a 20-page paper. Okay. But I'll at least go through the simulator code, and I'll at least let you know how the code looks like. Okay. So that you can understand from that.
Okay.
Some
Yeah.
insights from that. Okay. Any other questions? Okay, I guess we are good. We are running out of time also. Overall, it was an awesome presentation, to be honest. I think the best so far. So yeah, kudos to you and your team. Thank you. Yeah, we can start the next one.
Can you see the slides?
Yeah, but there is some noise coming in.
Okay, I think it's from the internal part. Can you still hear me clearly?
No, it's still noisy.
Okay, maybe then I will join from my phone.
Okay.
But can you hear now?
Yeah, now it's perfect. Can you share your screen?
Yes. Can you see the slides?
Yeah, maybe go for full screen. Yeah, cool. Yeah, it started.
Yeah, I'm Rahul Pagnikar and I am from teammate the Kachra set. And I am going to present the paper Timing Cache Access to Eliminate Side Channels in Shared Software. So the problem is that the traditional war between the performance and the security, and this has affected the shared software. And clearly, the winner here is the performance due to the very low memory footprint. Uh, you can just imagine what will happen if the shared software suddenly becomes private to each process, and then the DRAM will be overflooded, and there can be thrashing there also. And as the performance has become the winner here, so it has led to several security flaws. And the paper focuses on the timing side channel attacks on the shared software. And these side channel attacks have become the base for more sophisticated attacks like the Spectre and its variant. So the paper targets for the base of such sophisticated attack, that is the side channel. So if one mitigates the side channel attack, so the attacker won't be able to do more sophisticated attacks. And in the side channel attacks also, the paper focuses on the reuse of the shared data. That is the attacker needs to reload the data, not just keep on flushing it. And so why the need for this time cache? Because the existing methods on the non-shared data, that was discussed on Monday, the Caesar S, they are based on the randomization, and for the side channel attacks, the data is being shared. So the attacker anyway knows where the data is placed in the cache through the address, and so they do not work on the shared data. And the existing methods on this shared data, the paper talks about the cache partitioning, where the cache is partitioned for the processes, and the process gets some amount of sets, and the constant time algorithms, which restricts the timing information to the processes. So there are huge latencies here, and the partitioning cache also has this storage overhead, as the process now doesn't get the entire cache to work. So the time cache is proposed, and the highlight of this cache is that it is a combination of hardware and software. I will be discussing it in further slides. The next idea is that unlike the cache partitioning, which isolates the access on space, the time cache isolates it on time. So like it's said that lower katta hai. So similarly, the timing certain attacks will be mitigated by timing based solutions. And this time cache can work in conjunction with all other mitigation techniques that I discussed earlier, the cache partitioning and the mitigations for the non-shared data as well. And it has very low overhead as compared to what I have seen so far.
Low overhead in terms of what?
Sir, I shall be discussing in further slides.
No, that is okay. You will be discussing in further slide. But when you say low, in terms of what? Performance, storage, power, energy, area?
This is in terms of the performance. And
Okay, then maybe you should have mentioned low performance
time.
overhead. Yeah.
Okay. The main idea of the time cache is the first access. So the first access is defined as the shared data that was accessed first time by a process which was brought by some other process. And this first access is only of importance for the attack as far as the timing search and attack goes. And that's because the attacker monitors the first access only, and it is useless for the attacker to go for second, third, and so on. So the idea is that instead of serving the data directly from the cache, the idea is to delay the first access, and this delay is applicable to all the cache lines and is maintained for each process. So the process gets the illusion that
Do you have any animations or figure?
Yes, sir. Yes,
okay.
Sir.
Maybe jump to that. That will be easy.
Okay, sir.
Yeah.
I suppose I explain some terms before moving to animation. So these security bits track the first access of each cache line and for each process. So if the S bit is 0, then it indicates the process. It's the first access for the process, and these S bits are updated whenever the cache line is loaded or there is some activity on the cache line. Basically loaded or the evicted. The problem with the S bits is that it needs to be maintained for each process, and so they have to be stored and retrieved during the context switches. So there is a possibility that after the context switch, the process came and they changed the S bits for the cache line, and so when this process resumes, so its S bits may become stale. And so the solution to update these tail bits is the timestamps. So the time cache maintains two timestamps, that is the context switch timestamp and the timestamp when the cache line was loaded. And this is the design. So software maintains the S bits. The some the trusted software in the paper they have kept it for the OS itself, and for the hardware it maintains the S bits, the timestamps, and the requirement is that it requires comparators and SRAM array to update to compare the timestamps basically and to update the S bits. And this design has the overhead of nearly 0.3% as compared to the time slice that the process gets to run on the core. So this is the animation which simulates the flush and reload attack. So here's the victim and spy, and these are the set their as bits. Focus on these two lines. So this cache line has the S bit set, so it has already done with its first access, and same for the spy as well. So now this spy flushes the cache line. Then the S bits, since the cache line is flushed, so there has been activity in the cache line, and so the S bits need to be updated. Since there is no data, the S bits are set to 0. Then a victim tries to access the same cache line, and there is now a cache miss. So the request goes to the memory, and it's the regular process. The memory serves, and then the data is given to the victim through the cache. And now here, since the victim has accessed the data, so it has done with the first access, and so now its S bit for this cache line is set. But the spy hasn't accessed that cache line yet, so its S bit is still 0. And now when the spy tries to reload the cache line, since its S bit is 0, so it is the first access. The request goes to the memory even if the data is still in the cache. The memory responds to the data, and when it reaches the cache, that data is discarded. Since the data in the cache line is already the updated one, and then this data is given to the spy, and now its S bit is set to 1. This is how the time cache works, and it prevents the this flush and reload attack. Now coming to the evaluation, the paper discusses both security and the performance evaluation. So from the security perspective, the time cache is run on a parent-child scenario. The parent is the attacker, and it again does the same flush and reload attack. So the parent flushes and goes to sleep. Then child wakes up and it accesses the data, and again the child sleeps. The parent attacks by reloading it. And this is done in the Jumper simulator. And similarly, the GNU PG version of RSA, the same flush and reload attack is done, and they have done it on the simulator as well as on real machine. And in both the cases, they were able to mitigate the attack. And one more interesting point is that S bits do not add additional side channels. Coming to the performance perspective, so they have run on both Spec 2006 and Parsec benchmarks. This is the incomplete list for the Spec 2006, as the list won't fit in the slide. So I've cropped it. And as can be seen here, the average access for Spec 2006 is nearly 1.5 overhead for the first access. And for the Parsec, the first access overhead is around 1.2%. Coming to the LLC size sensitivity, this is the scaling of the time cache with the increase in the cache size of the last level. And as seen here, as the cache size increases, the execution time keeps reducing. It's around 2.5% here, is 1.6 here, and it's 1.7. And this has been run on the single bench on a single core test. So concluding the time cache, unlike the cache partition technique, the process can now utilize the entire cache, and this can work across the context switches and at the all cache levels. And the cross core and the same core attacks can also be prevented using the time cache. That's it. Any questions?
It was so quick. Yeah. Questions? Anyone?
Hello, Ajay this side. So I have a question where this S bits are stored, like where these S bits are maintained.
So these S bits are maintained by the software. Here in this case, it is OS. So it's most probably in the PCB, the process control block.
Okay. Each process maintain its own S bits array.
Yes, for each cache line.
But then how is it updated once a particular cache line is loaded?
Yeah. So basically, they compare it. So we have these two timestamps. The context switch timestamp and the cache line load timestamp. So if this timestamp is less than this load timestamp,
I got it. I got that. So that means these two registers are accessible to OS, is it?
yes. Not the load timestamp. The OS has the access to the context switch. This is maintained in the hardware directly.
No. So when you reset or set an S bit, you need to look at this counter values, right? The timestamp counter values.
Yes.
That means you should have the privilege to access both these registers, right?
Yes.
And this cache line loads timestamp is per cache line.
Yes, sir.
So that will be too much, right, in terms of storage overhead? Like you are
Yes.
storing timestamp per each cache line.
Yes, actually, however, they don't actually mention this space overhead in the paper anywhere. One of the negatives of the paper.
Arey, did this paper appeared in ISKA? Are we missing something?
No. They talk about the performance overhead with respect to
That's
time.
okay. Performance is okay.
Yeah,
It's a shared
but
library. It won't be much. Huh?
Yeah, but they don't mention how it scales with the number of cache lines or the number of processes in.
No, so I think I may be wrong, but I don't think we have this timestamp load timestamp counter per cache line. This is just a global counter. When you load a cache line, you look at that global counter. That's all.
No, sir. It is maintained per cache line as each S bit indicates it corresponds to one particular cache line. So
No, S bit is per cache line, but this timestamp, why you need it per cache line?
So if one of the cache line is evicted by a process, only that timestamp, only that cache line's timestamp needs to be updated instead of the global one.
See, timestamp is generally required to understand how much when the cache block came and when the cache block got evicted, right? Even with the global counter, we can still have an idea of that.
That's what. Why you need to store it? I don't think they are storing it. It's just a global clock, right? So whenever you need to access it, just look at that clock. That's all. Because otherwise it will be impractical. 64-bit counter for storing time will be like 8 bytes per cache line. So for a 64-byte cache line, you'll have 8 bytes of overhead. That will be too much.
At least that's what I understood, because they also mentioned the hardware solution in which they compare these timestamps parallelly.
Then you can compare timestamp parallelly because it's just a constant value, right? At a given point of time, once you read this register value, you can have hundreds of comparisons. That's not a problem.
No, I mean, let's see, one of the processes is updating its S bits. So one TS is compared with multiple TCs parallelly.
It's not really clear exactly. So and you are saying all these counters are per process.
The context switch timestamp is per process. S bits are per process, and the cache line timestamp is per cache line.
Okay, I think I need to read it.
Maybe I can show the hardware diagram that they have given in the paper. So this is what we got from it. So these are two threads, and this is the timestamp comparator, and each thread and there are 8 cache lines, and there are for each cache line there is timestamp, and for each thread for each cache line there are S bits.
Wow. I think that they are proposing some, highly optimized implementation. I think we should look at that. I don't think they are storing the timestamp in the tag array itself. What exactly is this transpose gate?
This is the optimized thing that so that the comparison can happen faster.
Okay. I think we should look at it. Can you update on Piaja by looking at it properly?
Sure.
This is also a comment for other groups. So there are a few presentations that we had last week. And the presenter said, yeah, I will update on Piaja, but it's been 10 days, no update. So do it by this week so that I'll grade your presentations. Okay, any other questions?
This timestamp comparator, it's in hardware where it is exactly sitting, and this TC0 to TC7, these are, you are saying these counters are maintained in the process per cache line. So those are in memory, and you have a latency for reading those values and then comparing. So
no, only this timestamp for the context switch that is in the memory, and that is maintained for each process. This is maintained in the hardware only. This TC timestamp.
So hardware, as Professor Bisser told, that it's too many per cache line, right? So
yeah, I think that he would look at. He would look at, and we can come back again. Okay. Yeah. So, any other questions? Okay. Can someone think to fool this idea? I just got the idea, but I'm not sure whether it's practical. But can you guys think about it? So you should come up with an attack where this time cache won't work. Basically, you have to fool the notion of S bits. Are you guys thinking of sleeping? So Rahul answered the simple trivial query. So instead of doing flush reload, if I do flush reload and reload, what will happen?
Yeah. So by that time, the second axis is right.
Mm-hmm.
Yeah. It is going to be hit for the attacker, but then. Yeah, it can be said that the victim had brought the data.
May not be right.
Yeah, may not be. Yeah.
Yeah, so we need to propose an attack where you have to fool the S bit and you need a guarantee that this access is because of victim, right? So that should be the ideal attack to fool time cache. So what if I have, multi-threaded attacker?
Yeah, multi-threaded means two process attacking one victim, right?
Two threads, one process, but two threads.
Okay, and one is spy and victim. Is that so?
No, so let me spell it out clearly. So let's say there is a two-threaded process. Okay, so you are maintaining the S bits per process, right?
Yes.
Yeah, so let's say I have a multi-threaded binary, multi-threaded attacker, and it's a two-threaded. That means there are two spy. Okay, and there is a victim as usual that's running. Will this work? This time cache? If I think it will work.
Yes, both threads will have different S bits.
No, they won't have different S bits. They are part of the same process. They will have same S bit. The attacker threads, they are part of the same process. So the PID is same.
Okay, then it is same as the last case. That twice reload.
Yeah, I was just trying to come up with a attack scenario where it will fail. So yeah, then I think it won't. Yes. Anyone has any other pointers? No. Okay.
Sir, just one question. So while I was reading the paper, I wasn't able to completely understand why a flush and flush could not fool it.
Okay. Yeah, I don't think it mitigates flush and flush, right?
They have.
Because in flush you don't reload, right? You just do flush.
Yes.
So you can go back to the same protocol, right? Let's say there was a shared cache line, and let's say the attacker tried to flush it, right? Will the S bit affect? No, right? There is no load now. Come on. So the S bit comes into picture because it tries to make sure that on the very first access, it goes to DRAM, right? Irrespective of whether it's there in the cache or not.
Yeah.
Yeah, so with the flush, it won't be able to do that, right? Because in flush, you are not bringing anything from the DRAM.
So, but okay.
I can't think of it, but it seems like it's not resilient to flush and flush.
Yeah.
Wow. Yeah, the other idea that I was thinking, maybe I should just spell it out. If anyone can think, that will be better. I was thinking, can prefetcher fool the time cache by sending a dummy proxy access, and then the attacker will come back. But again, the scenario will be same or similar to what we have discussed now. How will you ensure that this is from victim? Right? So yeah. Okay, so maybe we'll take it offline. So Devasis, you can stop recording.